Hello everyone, my name is Tigran and my capstone project is design and additive manufacturing of cycloidal gearboxes, empirical materials selection and system validation. I did my project under supervision of Arman Asatryan at American University of Armenia. So before we jump into the main project, let's now understand what is a cycloidal gearbox at all, because everything else depends on it. Cycloidal gearbox is a type of a speed reducer. Here you can see all the elements of it: high-speed input shaft, eccentric bearing, cycloidal discs, ring gear, and slow-speed output shaft. And how it works: the input shaft spins the eccentric bearings, which are attached to cycloidal discs. Cycloidal discs wobble inside the ring gear pins, and they rotate the output shaft. So the thing is here that cycloidal discs have one fewer lobe than there are pins in the ring gear, which makes it when input shaft does one full rotation, the cycloidal disc moves only from one pin to another one, which brings its key advantages: the high reduction ratios, low backlash, and high torque density in a small footprint. Here you can see my model that I created using SolidWorks software, and here you can see how it works inside. Oh, here it is from inside. Okay, so the cycloidal gearboxes are used in robotic joints, as you see in Daniel's project, automated system, and motion platforms. But if they are this useful, why don't we see them everywhere? Because industrial cycloidal gearboxes are created using expensive CNC machines, which makes manufacturing slow, expensive, and out of reach for students, small groups, and prototyping labs. Here is where the opportunity comes forward. 3D printing, FDM 3D printing is improving day by day, and it can print usable parts in just few hours. But the thing is, people don't know how people mostly don't know how it will act under constant load. So I want to change the guesswork into actual real test data to see if we can change the traditional manufactured cycloidal gearboxes into the 3D printed ones, which can be cheaper and faster alternatives. Okay, so the objectives and engineering targets. My cycloidal gearbox is dual stage, which means it have two discs inside, and it is for balancing the forces inside the cycloidal gearbox. The reduction ratio is 10:1. I set the torque target from 5 to 20 Newton meters based on the similar designs that reach to this torque, and the efficiency target is set from 70 to 75% because it is reasonable for a 3D printed cycloidal gearbox. So the method is to conduct 3 separate tests, each one focusing on one way where the cycloidal gearboxes can fail. The first one is a 12-hour creep test, which checks how much each material bends under constant load, because if it bends too much, it can arise permanent play in the gearbox. The second test is 5-hour wear test to check how much the surface of the materials wear under the constant contact with other materials. Which can, if it wears too much, it can bring precision problems in the cycloidal gearbox. And the last one is tensile test to check how much pressure each material can handle before it breaks. So here are the candidate filaments for my capstone project. The first one is carbon fiber, which is known for its strength. Second one is polycarbonate, known for higher rigidity. PETG, it's tough, but the most important thing here that it's very easy to print. Nylon, the most ductile one here, and I chose PLA for just common reference baseline um, because this is most known and most used filament for 3D printers. So let's jump into the first test. As you can see, I created and printed these C-shaped components. Each one has this gap between these two lines inside. And when you can see the setup, I hang 3.3 kilogram load from it, and after 12 hours I measure the distance between these two in this gap to understand how much does it deflect. So here you can see the results from these tests. You can see that carbon fiber was a winner here because it deflected only from 12 millimeters to 15.8 millimeters, only 3.8 millimeters deflection here. PEGI was second with 29.7 millimeter deflection, nylon third 37 millimeters, and PLA last 41.2 millimeters. And here you can see some visuals from these tests. The polycarbonate was broken before even hitting the 12-hour mark, which is a which can be considered as failure. And PLA halfly failed this test because, as you can see, the layers were separated from each other, and you can see how much small is the deflection in the carbon fiber after 12-hour constant load. So let's jump into the next test, the 5-hour wear test. I created this setup. I printed these gears from each material and connected them to the metallic gear in the middle, and connected all this setup to the motor, so it will rotate for 4 continuous hours to see how much each gear will lose in its diameter. So here you can see how the test looked like. The sound was very loud. I just moved it here. Okay, and here are the results from my wear test. The PEGI was winner here. It only lost 0.28 millimeters. The PLA and carbon fiber did similar job, only 0.5 and 0.6 millimeter loss, and nylon lost almost 0.9 millimeters, and polycarbonate was failed this test too because it divided into 2 parts, as you can see here, after 3 hours of rotation. So it failed here too. And let's jump into the slide is just disappeared from here. Okay, the tensile test. As you can see, with this test, I use this standard design, which I took from ASTM D638 standard. This is this design and the standard sizes for the test. Here you can see how test actually happened. This is nylon, and next to it is PETG, and okay, in the bottom are graphical insights from each test. Okay, and the results are following. Carbon fiber was a winner here too. It held up to 71 megapascal peak stress. The second was PETG, then polycarbonate 40.8, PLA, and then nylon only 24.9, which explains why it is so ductile material. So here are all the results from all the tests that I've conducted. You can see that carbon fiber was a winner at creep test and tensile test, and the PEGI was winner at wear test. Polycarbonate was disqualified because it failed 2 tests and was average in the third one, and nylon and PLA was not selected because they were average in each test. So Here is how I chose what material to use for each component. For structural zones, for the components that take the most pressure and most forces inside the cycloidal gearbox, I use carbon fiber because it holds up to 71 megapascal strength, and it had the lowest creep. I used it for cycloidal disc and output flanges, and for the wear zones where the contact happens the most, I used PEGI because it had only 0.28 millimeter loss in the diameter in the wear test. I used it for housing, input shaft, ring gear pins, and spacers. I also wanted to print the input shaft with carbon fiber because it holds a lot of force in it too, but I was not able to do that because carbon fiber was really bad at printing very small details. You can see an example here. You can take a look how it failed to print it. And here are all the components: cycloidal discs, output flanges, eccentric bearings, input shaft, housing, and the topping. And here is the final gearbox assembly, how it looks. So for the system validation, I did a pulley test. Here you can see the setup. I printed this pulley that you can see here, right here. I connected it to output shaft and connected it to the rod to pull some weights from it. And I also designed and printed this coupler to attach my gearbox to the motor. And after doing this test, I will be able to calculate the torque and the efficiency for my gearbox. Okay, here you can see the load progression. I went from 1.5 kilograms up to 27 kilograms, and I had some fails in between this test and improvements, which I'll show you in next slides. Here you can see the test in action, how it actually works. Okay, and the first fail occurred at 20 kilograms, as you can see in the video. The pins of output shaft were broken. As you can see it here, it's very small. It was broken into two pieces. And what I did, I redesigned it. I added a hole in it to insert a metallic rod to make it stronger and not to break. And the second fail occurred at 25 kilogram. After doing this improvement, I was able to go up to 25 kilograms, and at 25 kilograms another fail occurred. As you can see in the video, the input shaft was broken from the place that was the weakest, and after doing some research, I understood that printing it in 45-degree angle will make that weakest part stronger because of the layer layout. And after doing these improvements, I was able to lift 27 kilograms of load. And here are the calculations after this pulley test. I was able, my output torque was 8.21 Newton meters, which is within the range from 5 to 20 Newton meters, and my efficiency was 64%, which is approaches to the 70 to 75 target range. But I don't consider it as a failure because 64% is really a good result too for a 3D printed gearbox. And here you can see comparison between CNC machined and 3D printed cycloidal gearboxes. You can see the drastic change in the prices. Also, the CNC machine one has efficiency from 75 to 90%. Mine is 64, and the torque is 10 to 15 Newton meters for a CNC machine one, and mine is 8.21 Newton meter. So to conclude, I can consider my project as a success, and it can be used. And it can be used instead of manufacture CNC machines. That was what I proved here. And for the future work, it can be the model can be changed and added some motor to it and integrated with the actual robot joints, for example. As you've seen here, we can definitely do it, and that's for the future work. And the design can be modified a little bit so it will able to lift more load and bring the efficiency up. So that was it. Thank you everyone for your attention.
It's always very good to see something working and also being tested up to a break point. Very well done. What do you think of your material research? I've seen a lot of research with them, but have you explored every avenue, such as metal 3D printing or etc.? Because there are some enterprises in Armenia that do metal 3D printing, which is, in terms of cost, is comparable actually.
Yeah, so I didn't do that, and the reason for that, I wanted to use the resources that we have in this university so that the students can use this, can modify this, can use these projects in our labs. The main reason that I've done this project is that so it will be reachable for students and especially in our university. That's why I considered using only our 3D printers and bring the scope of materials to our 3D printer scope.
Yeah, but that's probably a general comment because the biggest 3D metal 3D printing shop in Armenia is a couple of 100 meters from here. Hybrid lab, if you know, but as an advice for everyone, make use of that facility. I'm not just advertising, but there are facilities in Armenia that you could use as well.
Yeah, that can be considered as a future work too, to just improve materials, components of this gearbox and just make it better. And I'll certainly take it as a consideration. Yeah, thank you.
About the application is, I believe it's like limited in education and research part. So, or you believe it's also applicable in industrial?
Yeah, not it. So let's say this was like the first step to this part of field, because I just created the gearbox, tested it to understand if it can be usable in that fields that you mentioned, for example, robotic joints or automated systems. And the next steps of, as I mentioned in the future work, in the conclusion, can be that, so it can be added to a motor and can be used in the robotic joints to be tested, to be understood what can be improved. And that's it, I think.
Okay. And then about the material, you mentioned that nylon and PLA, they got like average in each test.
Yeah.
It wasn't this clear from before doing the test.
Uh, It was so, as I mentioned, for PLA, it was clear that I took that material for the baseline. So all of the students here are using PLA for their projects for every class. So people know that how it behaves under some circumstances. So I took it for a baseline so people can understand how different materials behave and take it as a baseline. And nylon, I had huge hopes that it would do better actually, and but it just failed. Not failed, but it was not selected because it didn't good a great job for this specifically project for using in gearboxes.
So it's very good project, and I see that the result is also quite satisfying. And thanks for using our prototype in lab and also collaborating with.
Thank you too.
Thanks.
Thank you for questions.
How many times did you run the experiment regarding the material research? Is that one experiment with them, or you just run multiple experiments?
Do you mean this final
The previous one. So there you, yeah. For example, this one you are showing some results, and also the next one. Is that single experiment or?
No, I did actually multiple. So this tensile test I did with Raja Kocharyan, which I'm thankful for him. So we actually we used this tensile test for the first time. So we had to do some tests before actually completing the final test, so I can take the results. We use different standards. We use different components. This was the final one, but we use different ones to check what is the best one to get the results from. So we did multiple of them, but for the for example, for this 5-hour wear test, this was the only test, and for the crib one too. This one the only test, and for the tensile one, we did a couple of them.
Yeah, because in Yunnan you need to also do it multiple times and also take the average result and estimate the error.
Okay, got it. I'll take it into consideration.
So for the 27 kilogram test, it didn't break, right?
No.
Is it possible that your system can handle more? Did you just underestimated it?
It might be, but we were not able to lift it. The motor just not spinning anymore.
So this the motor failed now that you.
So the no, because the load was too much already, and my system here, as shown, I can show you here. In this calculation, you see the 42 kilograms is the theoretical maximum that my setup can lift. So that's the maximum, and I only was able to reach 27 kilograms, and also in industrial ones are able to go to efficiency from 70 to 90%. So I think being able to get to this efficiency is a
It's
good
a good result. I think maybe it could have lived to 28 as well, maybe even 29.
No, I checked them, but I failed to do that. So the 27 was the pick one. Okay, thank you very much.